In this problem, we're going to be given a set which has been completely listed out, and we are going to try to write that set compactly using an Elementhood test. So for example, here in part A, we are given the set which consists of the elements 1, 2, 4, 8, 16, 32, dot, 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 so that pattern just continues for forever. And we would like to write this set compactly using an Elementhood test. So the key to working these problems is to be able to figure out the pattern that the set that you're given follows. So if we look at this, it's not too hard to figure out what's going on. We see pretty easily that every element of this set is really just 2 raised to some power. For instance, the number 1 can be written as 2 to the 0 because 2 to the 0 is 1. And the number 2 can be written as obviously 2 to the 1. And the number 4 is just 2 squared, and the number 8 is just 2 cubed. 16 is 2 to the 4th, 32 is 2 to the 5th, etc. So this original set we see has a very nice pattern. It's just 2 raised to some integer. So we can go ahead and write that using an Elementhood test very compactly. In general, each one of these elements has the form 2 to the n, where n is a natural number because the natural numbers consist of all the integers 0, 1, 2, 3, 4, etc. So once I identify this pattern, I can write that as my set. Basically, this is the set of 2 to the n, and then here's where I put in the Elementhood test. So it's the set of all things 2 to the n such that n is a natural number. So instead of writing out this infinitely long list of things, I can write it compactly using this Elementhood test. So there's one example. Let's do another one. Part B, we're given -2, -1, 0, 1, 2, and 3. So this one in some ways is a little simpler. It's a finite list. We don't have to go on for forever. And this isn't too hard to do. There's actually a very easy way to do this. We see that this is just a set of integers, right? -2, -1, 0, 1, 2, 3, those are all integers. So it seems to be pretty obvious we should probably use the set z, which consists of all integers z. The only difference is z goes up for forever, right? It includes the elements 4, 5, 6, 7, 8, 9, etc. It also includes a lot of negative elements, -3, -4. So even though we are probably going to want to use the set z here, we need to restrict the values to contain just the values that we see here in our original set. So we're going to construct our set by choosing all of our elements from z, so that's kind of the pattern in this case. But we need to choose it such that we satisfy this Elementhood test. So I am going to make my set consist of all elements of z, but under the condition that they must be greater than or equal to -2 and less than or equal to 3. So this basically takes my set z and narrows it down to just this set of elements. So that one was pretty straightforward. Let's do another one, part C. Consider this set. So it continues forever to the left and forever to the right, and it follows a pattern -8, -6, -4, -2, 0, 2, 4, 6, 8, 10, 12, 14, etc. So after we look at this, we can kind of figure out the pattern pretty easily. Everything here is just some multiple of 2. 2 times a -4 is -8. 2 times a -3 is -6. 2 times a -2 is -4, etc. So this has a fairly simple pattern, and now that we see the pattern, we can go ahead and write down our set. Everything in this set has the form of 2x. It's 2 times some number. The question is, what should that number be? Should x be a real valued number? Should it be an integer? Should it be from the natural numbers? Well, here we need to use more than the natural numbers because we are using negative integers over here. So it definitely needs to be from z, the integers. So this is how we can write this set compactly using an Elementhood test. And then let's go ahead and do one more. This one's a little trickier to figure out the pattern, but once you figure out the pattern, it's easy to write down using an Elementhood test. So here's the set. It consists of the elements 3, 6, 11, 18, 27, 38, dot, 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 so that the pattern just continues for forever. Figuring out this pattern is a little tricky. Once you see it, though, it's not hard. And the pattern is this. The first element can be written as 1 squared plus 2, because 1 squared plus 2 is 3. The second element can be written as 2 squared plus 2, because 2 squared plus 2 is 6. 3 squared plus 2 is 11. 4 squared plus 2 is 18. 5 squared plus 2 is 27. 6 squared plus 2 is 38. So every single element is going to have the form of n squared plus 2. That's what's going on in the pattern. So I can easily write that as n squared plus 2. And now we have to ask ourselves the question, what value can n take on? And the work that we've listed here, it took on the values 1, 2, 3, 4, 5, 6, etc. So it seems that we should use the natural numbers because the integers would include negative values for n, and we don't want to include that. However, the way we would define the natural numbers does include the element 0, and we didn't use the element 0 over here. The smallest element we used was the element 1. So we probably need to use the natural numbers, but we don't want to use 0. So the way we can indicate that here is we can say our set consists of all the elements of the form n squared plus 2 such that n is in the natural numbers except for the point 0. So we've used our set difference to say take the natural numbers but remove the point 0 from it. So that is sometimes a useful thing to do when you're trying to do Elementhood tests. If you need to use a set that's already been defined like z or n or r or q, but there's one point that gives you a problem, you can use the set difference operator to remove that point and compactly write your set as needed.